Okay, we're here with going to do the first lecture. Maybe there'll only be one, but no more than two on the AC/DC circuits. Now, a lot of this we covered a couple of weeks ago here with the headsets because they said didn't have good enough sound control, so we'll try it this way. But I'm basically going to do the lecture for AC/DC. I'll review some of the AC stuff only as we go, but the very first lecture on AC, you got to be familiar with that on your own. Then there'll be two labs, but those will be separate and separate videos. All right, so in this lecture, as I said, we're talking about AC to DC, and that means rectifier circuits. So, so what we're talking about is electric power conversion. Okay? So what have we got? We have four different ways this can happen. We got DC to DC. We have some DC voltage. We want to regulate it to some other DC voltage. 12 volts becomes 5 volts. 24 volts, like in a car battery or something, can become 6 volts or 12. Okay, so that's a process of regulation, but you start with DC and you end with DC. Presumably what you're trying to do is take very noisy, rough DC and make it very smooth at a constant value. There's what we're going to talk about in this lecture, AC to DC. In other words, you plug something into the wall and out comes DC. We use these in chargers, wall chargers, all kinds of things. You plug in an appliance, a television, you plug it into the wall, but inside that's quickly converted to DC to run, the digital electronics, for instance. You can go the other way, start with DC and go to AC. This is called an inverter, obvious reasons. You're doing the opposite of AC to DC. I've tried these once. I had one, and we were using it actually in a job that I had, and I could just attach it to an automobile battery, use jumper cables attached to the automobile, and I'd get 120 volts AC out of it, and ran power tools out in the field. Right? All you got to do is keep the car running, so you don't just draw the battery down. Pretty easy there. Then there's AC to AC. In other words, you don't change the shape of the signal. You have alternating current in, alternating current out, but you might change the value of it, just like DC to DC. And you might control how much current can be supplied, that sort of thing. Here's a circuit we're all very familiar with. We plug these into the wall all the time. This right here being the usual wall wart. Right, you plug that in. It's been opened up. This is what's inside. So this thing right here, with 2 leads going in and 3 leads coming out, that's the transformer. That's this thing right here. And I talked about those last week in the transformer, and that lecture is available and those labs are available. I think I sent the slides out to you. The other big piece that's here is this diamond shape of diodes. Okay, and I'll talk about that later. We're going to do that in the lab, the first of 2 labs on AC to DC. And then there's a capacitor here that smooths the DC out. And we saw a little bit of that when we did a capacitor circuit, right? And I had you time it with your watch and see how long the capacitor could hold the charge, as long as you don't charge it up. We just use that same gimmick to what we call smooth out the DC. All right, so let's see what happens here. On the far left side, we've got the AC source. This is like plug it into the wall, right? The wall. the wall socket. You just plug it in, right? Then the transformer doesn't change the shape at all. We learned that. But it changes the magnitude. It changes how high the peak is, right? Now, there's not a lot of difference here, but this peak is different from that peak. They don't look a lot different in the pictures, but the vertical scale is quite a bit different. So this is a lot smaller than that. All right, then the next step is it goes through this rectifier thing here, this cycle of diodes. And I'll walk you through that after a few slides here. And basically what that does is say, okay, nothing's down here anymore. I flipped all the downsides up. In other words, it's like I drew a line through here, and I flipped this up to here, flipped this up to here, flipped this up to here, and so forth. So I filled in all the positive holes, and there's nothing now that's negative. So then all I have to do now is somehow get all this positive stuff to be smooth, like to flatten it out, and that's the job of the capacitor. This is actually, this roughness here is actually all these little bumps happening and hitting it. And the capacitor just stores the voltage, stores the charge, and acts as a little short-term battery till the signal comes around again. Okay? So just to remind you about diodes, remember there's 3 important characteristics. First one here is that when you turn them on, it takes at least 7/10, sometimes 6/10 of a volt to turn them on. Sometimes it takes even more than a volt. And that's true when the diode is an LED. Different colors take a different amount of voltage to turn on. Then there's this reverse voltage. If I put the voltage on backwards, I turn the diode off and it's like an open circuit. It's like this. So between this plus 0.7 and backwards, we can use the diodes as a switch. A real cheap and easy switch that allows current and then disallows it. And then if you reverse it a bunch, you likely destroy the diode this way, okay? And you remember these diagrams, you've had them in the lab, where this is the positive end, and this is the negative end. We call this the cathode. And a lot of these terms, boy, they started from way back in vacuum tube days. I'm not sure anybody anymore remembers vacuum tubes. This is the anode. And they were literally pieces of metal pushed up into a glass tube like a light bulb that had a vacuum, or maybe had a gas in it, a special gas. So this was that curve. You've seen something like this, several times. Here's that 7/10 of a volt here, right? That little voltage, which once I pass it, it turns on. And so we often think of the diode as being, it does nothing, and then and then it turns. What's wrong with my hand sticking on the glass? And then it turns on. Well, I'm making a mess. Turns straight on. But really it's got a little bit of a curve to it. I'm not sure what I was doing there. All I wanted to do was draw a straight line and my hand got stuck on the tablet. Okay. In the reverse direction, there's no current flows. All I'm trying to show you is we think of the diode this way. I'll extend this down. We think of the diode this way. It's off, then it's completely on, and this is 0.7. And then if I go too far back, it's breakdown. Break it. Okay, this can often be quite a bit. You see in the figure here, they've got 1,000 volts. Sometimes we make the diodes to put this point at a very specific number, and we use that as a voltage regulator. It's kind of cool. In that case, we designed the diodes so that they don't destroy themselves. Okay, and I think we did this back before the midterm, where I show you the 4 cases when the battery voltage is less than 7/10. This may be positive and that negative, but it's not enough. So it's forward biased, but it's off. So this looks like an open circuit because it's not conducting any current. And if there's no current, then this voltage is 0. Okay? Doesn't matter as long as there's no current. The same is true in the reverse direction, but we'll get to that. Now, if I turn the voltage up a little bit further, which I'm done here at 5 volts, this gets more positive than 7/10 of a volt. And so the 7/10 of a volt appears at it. Now the voltage here doesn't keep growing. Remember the curve, the one I drew so badly several times, it actually, once the diode turns on, it's on. And we don't think of it as having a voltage drop other than 7/10. So if I do Kirchhoff's law around here, I go +5, minus 4.3, minus 0.7 is 0. Okay? You can go around the other way, but either way, you're going to have 5 minus 0.7. All that voltage has to appear on the resistor. Doesn't matter what size the resistor is. So the resistor then is always going to have 4.3 volts on it. It better be big enough to limit the current, right? Because if the resistor is R, the current here is 4.3 divided by R. And the diodes have certain voltages, certain currents that they will self-destruct on. So you need some resistance in there, but they're usually pretty sturdy. Okay, then there's the reverse that's off. So we're in that flat part of the curve on the negative side. So all that happened here was I still have positive voltage. Now it's 10 volts. But I flipped the diode around, right? You notice here the anode is down here. That's the anode and that's the cathode. Whereas over here, that's the anode and that's the cathode. Okay, so that turns the diode off. And then if I just turn the voltage up in the wrong direction, I break it. Okay, assuming it's the kind that's going to break down. So now let's do this with AC to DC. Let's look at power supplies. Power supply circuits convert an AC line voltage to DC voltage. And they reduce the AC voltage generally to a lower value. Not many DC circuits run on 100 volts or thereabouts, the kind of stuff coming out of the wall. If it is, there'd be a lot of warning labels on it and stuff, because 100 volts of DC would have a little bit of pop to it. Oh, to you. Okay, so that's the simple sole purpose of power supplies. Converting AC to DC at a lower value. All right, several ways to do it, and that's what we're going to do in the next 2 labs. 3 ways. The first is called a half-wave rectifier. Simple circuit here. 1 diode, an AC source, and a load. So this is a single loop here, going around here. Current will flow in this direction. This is electron flow. This is our current flow. The voltage will appear across the resistor, and all is hunky-dory as long as the voltage from the power supply is positive, like this, as long as it's doing a positive cycle, right? So the first half is simply this. Only the positive cycles pass through. Right? Other than that, on the negative side, look what happens. I've got if I put a minus voltage here and a plus voltage here, which is what happens when the source goes negative, right? I'm looking down at this part now. So this side is negative, negative. The diode is off. So it's like an open circuit. So we get 0 volts out. Okay? So what that amounts to then is, in the completed picture, this waveform, which is what comes out of the wall. Where's my pen here? This waveform right here gets converted to this waveform. Now notice this peak is the same as this peak. We haven't done anything DC yet. Haven't done anything DC. All we did was throw away the negative, the black parts of the waveform. Okay, that's all that happened here. Now if we added a capacitor on, it would smooth all this out. It would sink a little bit, then it would build back up, and it would smooth all this out. But it's got to wait a long time here before it gets another pop of energy. It's sort of like we're throwing energy into the capacitor, and the capacitor has to hang on to it on its own, and we got to throw some more in. Okay, that would be the case. Where am I at here? If I come across here and put a capacitor on there. Okay, this would cause that red smoothing. So now let's look at, nobody builds these except as the first experiment in lab. The parts for these are too cheap to not do it right. All right, so the next step is this. We go to, this is the picture you had, or I gave you at the beginning of the talk, which is the wall wart. The only thing that's different between this picture and the one you have is right here. There was a transformer in here. And we'll talk about that when we do the lab. But right now I'm just hooking up a 10 volt source directly to this diamond pattern of diodes. Now this is typically how it's drawn, and this is thought to be a ground. This point is connected to this point. It is not connected to this point, even though if I were to hook up the power supply, there'd be a black lead here and a red lead here. This black lead is not meant to be that. We'll talk about that more when I get to the experiment. All right, so I'm going to make that clear when we talk about it here, I'm going to change the picture. I'm going to change it to this. Okay? So what did I do? I took away the capacitor and I simply connected those two ground symbols like this. So these wires are not connected, they're just crossing. So this is the actual circuit that the bridge rectifier is talking about. And it's a bridge because look, by connecting this like this, the resistor is basically just running from this node over to this point. It leaps across this diamond pattern. That's where the name bridge comes from. All right, now how does it work? Let's see, there's a whole lot of diodes, and what are they going to be doing? Flipping and flopping all over the place. So let's take this first half when it runs, take that off, when it runs through the positive half cycle. So what have we got? At this point, this is positive and this is negative during this first half cycle. So let's trace that over. This is positive. So that means this point is positive and this point is negative. So let's just look at each of the diodes. If I have a positive here, and this point is always going to be more positive than any other point in the circuit because it's directly attached to the source. So that means this diode is on. The positive attached to the cathode is totally backwards, so that diode is off. Okay? Now we don't know about this point yet, so let's keep going around here. So if this diode's on, then that means this point is positive minus 0.7 volts, right? It took this value and subtracted 7/10 from it, and there it is. But it's still positive. So that means this side is positive, so this diode is off. Okay, let's trace it around. All we got is this one more diode to figure out what's going on there. So if we take this positive, we may get some voltage drop here. We'll get some, but basically this lead wants to stay positive. So here we come around here with the positive. So this is positive. So this is positive, and this is negative, so this diode is on. So, but wait, if this side is positive, why isn't that diode on? Because this positive is more positive than this. This side, what will I call it? Positive A and positive B. And positive A, I'll just write it up here, positive A is greater than positive B. So it keeps this diode turned off. So during the first half cycle, we have here comes the current. Where's the loop? Here's the coming down here. Now we go through this diode. Now we go around through the resistor and back through that diode and into the bottom. So we got a complete loop. Okay? Now just for fun, let's see what happens if I turn this off. If I flip to the bottom half now, and maybe I can change the pen color. Wouldn't that be interesting? Let me try, oh boy. Looks like I could try green. Is that going to work? The ink color? I'll try blue. Let's see what happens with that. All right. I haven't tried this before, but let's see. So now we're working down here with this part. Okay. Oh, look, it is blue. So now we're on the bottom side. So now this is negative and this is positive. So let's trace that through. The negative is over here, comes over here, negative. Negative here. So this gets overridden and it turns the diode off. The negative here, that's going to be the most negative spot in the circuit. So that's going to override this and turn that diode on. Okay, so what have I got here now? Negative keeps going around here. The negative here is, this is negative. And it's going to be more, oh, look, the bottom side of that is positive coming from here. This has gone positive. So that means this diode is going to go on. Okay, we'll see how this is, if this holds up or not. Boy. So that diode's off. Here comes negative, negative, negative is coming around here. So this side is now negative. But so that's going to turn this diode off. All right, and negative is here. So the only question we've got is, are these new negatives? Oh, wait a minute. I'm sorry. This is positive because it's attached just to that. So the only question we got is, how is this negative compared to this negative? Well, this is the source negative, so it's always going to be more negative than this, right? So once again, negative A is going to be less than negative B. You can think about that. So that diode is going to stay on, even though the voltages are all negative. It's the difference between the two sides that determine whether it's on or off. Okay, so there we are. And we will end up creating a waveform. All it did was convert the sine wave, into all positive peaks. Right? So those bottom ones all got flipped up. And now when we put the capacitor on, That's there to smooth things out, and we end up with this kind of picture. So here's that same circuit I just did. The same circuit right here. We just analyzed this. And here we are with our complete voltage. And here's the capacitor. The capacitor kicks on here, and here, and here, and here, and everywhere, right? So this is smoothing faster than the half wave because it has all the little peaks in there. So we call that a filter, and it's often running real well. Here's one we'll look at next week. Since we just did transformers, this takes advantage of a center tap transformer, Humberto, where we got a center tap. And remember what happens here now. These two sides, this and this, are 180 degrees out of phase. So as you might guess, if this is positive and this is negative, right, or ground we can call it, then this diode turns on. But this diode would turn off because I've got a positive signal over here and negative here. Then when I get to the bottom half of the sine wave, the signals reverse. The signals reverse. When this one is going up, this one is going down. And when this one is going down, this one is going up. So what happens is each of these two halves operate only during the plus portion, but the plus portions are exactly out of phase with each other. We'll talk about this more during the actual experiment for that in 2 weeks. Okay? So here's a link to a video that might be fun to watch if you can get that to run. It's actually a fellow talking, and you may get some other insights with that if you want. But this is it for this lecture on AC to DC. This is all I'm going to lecture on AC to DC. I'll be talking through more as we do labs with all three of these circuits, with 1 diode, 4 diodes, and then the 2 diodes in the center tap transformer. Okay? So we'll see you at those.